Hi, I'm Paul Kassebaum, the technical director for SandboxAQ, and I'm going to talk about what is quantum information. First, up front, I'd like to say that I was greatly inspired by the works of Chiara Merletto. On the left of the screen here is a popular science popularization of some of the ideas I'm going to be covering in a book that she wrote called The Science of Can and Can't. I highly recommend anyone who has even a cursory interest in this stuff to read this book. It's very approachable. And it's a popularization of some more complex explorations of these ideas. And on the right is a detailed technical version of this material, far more technical than I'm going to present, called The Constructor Theory of Information, published in the Proceedings A of the Royal Society, and it was co-written by David Deutsch as well as Chiara Merletto. So this is a variation on a theme by Chiara. So on my screen here on the left is the recreation of the Rosetta Stone with three different scripts saying the same thing. And on the right is a cartoon of DNA. And in some sense, both of these images are depicting information. But these are all really radically different things in the physical world. Even just on the Rosetta Stone side, each of the three scripts looks radically different. But in some sense, they contain the same exact information. So I think that a lot of folks, myself included, when I started looking into this, would assume that information must be a very abstract thing that would be very hard to put your hands around. But quantum information came from thinking about, can we have a physical theory of physical information? The great success of information technology that we have in some sense is really due to the great work that was done to abstract information, to create like Claude Shannon's information theory. But perhaps we threw the baby out with the bathwater. In other words, we abstracted it too far away from the physical reality. So in the 1970s, some physicists started to ask, what if we put physics back into a theory of information? And in particular, what happens if we put quantum physics into that theory? So in this talk, I'm going to talk about the physical theory of information and how quantum information falls naturally out of this physics-based theory of information. So to start, I'll discuss a physical concept of computing. What does it mean to compute? Well, first you need a physical object. In this case, I have a couple of photos of my computer's power cord. And with that physical object, it needs to have some property with at least two values that you can reversibly go back and forth between. So I've chosen the property that's reversible of whether or not my power cord is knotted. It's knotted or not knotted. And by permuting between these reversible values of some property, that is physically computing. And with this understanding of computing, you can then understand better what is data or information, physical information. So if you have two physical computers, I have my power cord for one computer and a power cord for another computer on the right there in black and white. And if I can make a one-to-one relationship between these reversible permutations of values from one physical computer to another physical computer, that relationship that I'm carrying over from one to the other, that thing that I'm copying, is information. And there I was showing two computer systems that were very similar physically, but this idea can work between other physical systems. The key is not that the two physical systems be of similar type, it's just that they have a property with reversibly permutable properties. So in this case, I have a power cord knotted or not knotted, and a coin heads up or heads down. Now, when I started looking at the theory of quantum information, I was coming at it from the perspective of a pure theoretical physicist with not a lot of experience in quantum, not a lot of experience in information theory. So I naively thought, for example, in this photo of a deck of cards, I naively thought that the information contained in this photo, it would be enough to say that I drew the Queen of Hearts. What I learned later, studying this material, was that actually you need to also understand what could have happened instead. So it's not enough to say that I drew the Queen of Hearts. You also need to say that I could have drawn any of the other 51 cards in the full deck. By the way, this is a deck that was produced by a good friend of mine, Russell Huffman at IBM. It's a collection of 53 or 54 different artists who design each of the faces. So the idea here is that information is actually contained in a full counterfactual statement. This happened, but all of these other alternative things could have happened. And that is an allusion to Chiara's title of that book, The Science of Can and Can't, the Counterfactuals. So to demonstrate another similar but different counterfactual, here's another one. So I drew the Queen of Hearts. This time the counterfactual would have been, I could have drawn any of the other queens of the different suits, right? And so this is meant to show that I drew the Queen of Hearts does not contain information by itself. You need to know what could have happened instead. So far, I've been showing examples of a computer and information and counterfactuals that are using physical systems that obey so-called classical physics. In other words, quantum mechanics is not playing a role in any of these systems here yet. So I want to now introduce quantum system to play these same sorts of games with. But I also want to make sure that I still stay within the realm of things that are tangible and easily accessible for people who are not in highly capable physics laboratories. So something as easy to get your hands on as a deck of cards. So for that, I'll use polarized sunglasses, and this is a silly photo of me wearing polarized sunglasses. And the as ubiquitous as polarized sunglasses are, they're actually giving you access to a quantum property of light. You may be familiar with the color of light, or the frequency, or the wavelength, or the energy of light, or the speed of light, or the direction of light, all these different properties. And your polarized sunglasses allow you to play with another property you may not have heard of, called the polarization of light. And that property is especially understandable through quantum mechanics. So let me demonstrate what you can do in perhaps your kitchen to get a sense of what polarization is. Here is a photo, is a video I'll play in a minute, of a bowl of water. And behind the bowl of water is a standing lamp. And in the surface of the bowl of water, you're seeing the reflection of the standing lamp light bulb. Now, when I play the video, I'm going to put my sunglasses between the camera and the reflection of the light bulb in the surface of water, and I'm going to turn my glasses, rotate my glasses around, and take a look at just that light bulb's reflection. You should be seeing it dimming or brightening as I rotate my sunglasses. Okay, so what you're seeing there is that the light that gets through my sunglasses after it's reflected off the surface of the water depends on this quantum property, the polarization of light. And water and air interfaces, or other interfaces like air and glass, for example, the reflection and the transmission of light through those interfaces will depend on polarization. And whatever polarization is, that video should give you an inkling that it has some sort of directionality to it, since it depends, since you were seeing things change, the brightness was changing depending on how my sunglasses were rotated. Here's another demonstration of the plastic films. These are called linear polarizing films that are attached to your sunglasses. You can order these films online and play around with them, cut them up into pieces and play around with them. And here I'm going to show you two films and how they interact with each other. So first I'll hold up a single film, then I'll hold up a second film behind it, rotate them relative to each other. And you see when the brightness again changes. And there's something interesting is happening in all three of those phases of the video. In the first phase, let me see if I can play the video again here and pause it. Yeah. So right away, something interesting is happening, even with just one of these films. These films are stretched when they're manufactured. And so that stretch sets up a special direction in the film. And right away with one of these films, the light that gets through them is dimmed by about a factor of a half, or 50% of the light gets through this film. Then when I take a second film, and no more light gets filtered, even though there are two now. When that special direction in the film caused by the stretching and the manufacturing, when those two film special directions are parallel to each other, no additional light gets blocked here, which is interesting. And then when I start rotating those special directions relative to each other, when those special directions are perpendicular, any light that got through the first one is blocked by the second one. Right. So there are a couple of, all of those things that I stated are actually very interesting if you start to try to think about how that's happening. What's the physics here? One way to think about the physics of any phenomena you're not already familiar with is to try to think through a metaphor. So there's whatever polarization is, you could convince yourself with what you've seen so far that is directional. So let's think through a metaphor of something else that's directional, like toothpicks. So the orientation of the toothpicks as I drop them randomly on a striped rug, I'm going to try to make a metaphor here. So the toothpicks are the photons. The orientation of the toothpicks relative to the stripes in the rug is like the polarization of the photons. And that's the stripes in the rug are setting up a special direction, and the rug is like the special direction in those linear polarizing films. And perhaps whether each photon or toothpick, each photon gets through the plastic is metaphorically similar to how aligned the toothpicks are to the rug's striped special direction. So suppose, going along with that metaphor, there might be some range of angles. That range of angles of the toothpick in the red arcs there, maybe those ranges of angles are parallel enough to the rug's striped special direction, enough to get through. And perhaps the blue range of angles or orientations of the toothpick are not parallel enough to get through the rug. And if this is metaphorically related to what's going on with polarization, then we should expect that the dimness factor that we were seeing should be related to the length of either these red arcs or these blue arcs divided by the full circumference of the circle. That ratio should be related to the dimness that we were seeing. And to remind you that the single film case is dimming the light by a factor of a half. In the case of light sources like the sun or certain like incandescent light bulbs. So another way to think about this is the length of these arcs has times the density of states. In other words, how many different orientations are allowed along that arc. Another way to see that this ratio should be the same as the last one is that density of states divided by density of states is just 1, right? So now when you take a density times a length, you should get some number. So those densities of states times the length of those arcs, or the full circumference, should give you a number of states. And it should be the number of states that pass through divided by the number of all possible states, is what these angular arcs of these toothpicks should be telling you. So if this is metaphorically correct, then let's say the red arcs are the ones that get through, and the green or blue ones are the ones that get blocked. So the red arcs are a relatively small portion of the full circumference, and it's significantly less than half of the full circumference. So if this was our theory of what's going on, our theory would be predicting that the dimness factor would be some small number, less than a half, less than what we observed. So that seems to be wrong. On the other hand, if we've said, well, maybe it's not the red arcs, it's the blue-green arcs, then that'd be some number significantly greater than a half. Again, not what we observe. So something's awry here. And what is it? Is it the math? What's wrong with the metaphor? It turns out that the math is not correct. The math is correct, but there's a fundamental assumption going on in our calculation here. We're assuming that the polarization of the light can be any angle, because the toothpick's orientation can be any angle. In a sense, we're assuming that that denominator there, the number of possible states, can take on any angle along the entire full circumference of the circle. But what we observe is that this ratio should be 1/2. So we can question one of the basic assumption that we should question is that any angle of the polarization is allowed. So what's an alternative assumption? An alternative assumption would be perhaps there are only two possible orientations of the polarization with respect to the special direction of the film. This switching of that assumption that the polarization could be any angle to the assumption that it can be only one of two angles is like playing around with a counterfactual. Think back to the deck of cards. I drew the Queen of Hearts out of 51 other cards in the one counterfactual, or I drew it out of just all the other queens of different suits, a smaller set of counterfactuals. So perhaps the problem here in our metaphor can be solved by switching counterfactuals. Okay, and that would give us that's a way to get the correct number, the observed dimness factor. The number of, if there are only two possible states for the photon's polarization with respect to the film special direction, only two, then only one of them can get through. And then we would, using the same reasoning in this slide here, the number of states that pass through is 1 divided by the total number of possible states is 2. We would get our half. So this switching of counterfactuals to fix this metaphor from assuming that the polarization can vary smoothly to the assumption that the polarization can only have two possible values, this or that, smooth and continuous to discrete and finite, that's what's called the quantization of a property, the quantization of the orientation of the photon's polarization. That's where the word quantum is typically comes from in quantum theory. So that probably sounds crazy. It sounded crazy to a lot of physicists in the early 1920s and so. So let me give you a little bit more evidence. There's lots more evidence than what I'm going to show you, but let me give you another reason to believe the quantization hypothesis. Here I'm showing the two sheets or two films with their special directions perpendicular to each other, blocking all the light. Now, I would ask you to think about what might happen if I took a third film and slipped it between these two films at an angle that's 45 degrees relative to the other two. That is, the third sheet's special direction is 45 degrees to these two sheets' special directions. What might happen? Will it look the same, that all the light that was blocked with 2 is still totally blocked with 3 films? Or does something else happen? Does more light get through? And if you've never seen this before, the results might shock you, right? It shocked me when I first saw it. So when you slip that third sheet through, more light gets through, even though you have more sheets. And one way to understand this, and really the only way to understand this when you start thinking about what's happening with each individual photon, is that you have to accept that quantization property again. It makes, at least the quantization property is consistent with what this counterintuitive behavior. So one way to think about it is when a photon comes from the light bulb, hits the first film, the film acts sort of like a bouncer at a club and asks the photon, hey, whoa, wait, before I let you through, I have a question for you. Are you parallel or perpendicular to my special strain direction? And the photon might say, well, we might intuitively say, well, maybe it's neither. But that quantization principle says it has to be one or the other. Okay, so it makes some choice. Then it comes across the second film. And that second film, in the 3-film case in this photo, where there's light getting through all of them, it hits the second film that's 45 degrees to the first one. That second film, again, asks the photon, whoa, before I let you through, I've got a question for you. Are you parallel or perpendicular to my special strain direction? Now, intuitively, we would say, well, the photon got through the first sheet, so its polarization must be parallel to the special strain direction of the first sheet. So the answer to the second bouncer's question intuitively would be neither. It should be neither parallel or perpendicular to the second sheet's special direction. It's got to be 45 degrees. But the quantization hypothesis, again, it says it only has 2 choices. All right. And so what ends up happening is that photon needs to answer one or the other, and it does so randomly, probabilistically, but not chaotically. I'll show you in another slide or two that we can predict the probability at which it makes that choice. But it makes a choice, parallel or perpendicular to it. Then it gets through. So any photons that get through that second sheet, again, see yet another bouncer in the third sheet, who again asks, are you parallel or perpendicular to my special strain direction? And again, our intuition butts up against what we observe. That photon will again answer one of those 2 strange answers, again, probabilistically, randomly. And I chose this special direction, the special angle of 45 degrees for all 3 sheets, because that probability is a half. There's a 50% chance that the photon will choose parallel, or 50% chance it will choose perpendicular. So in each case, the odds of getting through each successive sheet is a half. So the first sheet, there's a 1/2 probability of getting through. The second sheet's another half probability, another half probability. So overall, we see a dimness factor of 1/8. So that strange counterintuitive quantization hypothesis gives us an answer that's consistent with what we see. Again, the fully blocked case on the top left of that photo doesn't challenge our intuition, because the 2 directions of the sheet's special strain directions are perpendicular. So any photon got through the first one can give an intuitive answer to the second bouncer's question and say, well, I'm parallel to the first guy and you guys are perpendicular to each other, so I'm perpendicular to you all the time. Right? Now, again, I said that the photon is making these choices randomly, but not chaotically, that we can predict the probabilities. And I just showed you one special angle relative angle between two sheets. Let me show you what the odds are for all the different angles. So in this picture, this is a so-called polar plot. So in the red curve here is showing you the probability of a photon that got through one sheet to get through a second sheet when the two sheets are at some angle relative to each other. Along the horizontal axis is the case where they are parallel. The two sheets are parallel to each other, so the angle between them is 0. And so here I'll draw a little mark here. So when the two sheets are have their special strain directions parallel to each other, you can see that the red curve intersects the horizontal axis at a value of 1. In other words, the probability of a photon getting through both sheets is 100%. And then I told you that that there was the special angle I showed you with the 3 sheets was having each of the sheets be 45 degrees relative to each other. And again, you can read off where the red curve intersects that blue line at a half. In other words, 50% likely to get through. And then there are the special cases where things don't seem to be acting randomly. When the sheets' special directions are parallel to each other, the likelihood of the photon getting through is 100%. Anything that got through the first will absolutely get through the second one. Or what we're seeing with our eyes, I should say, we're seeing observational statistics of asking this question many, many times of all the billions and trillions of photons that are getting through the sheet as we look at it every second, right? So, and then there's the other special angle where things don't seem to be acting randomly, is when the two sheets' strain directions are perpendicular to each other. That red curve goes down to 0 likelihood of getting through both sheets. Every other relative angle between the two sheets is some other probability that's not 100% or 0%. The cases in where the blue marks are and all the other cases, these form two families of behavior that are helpful to think about or to hold in your mind. These two classes. The one class is where things are don't seem to be behaving randomly. In other words, seem to be behaving deterministically. And in the other case, where they are behaving randomly. So Chiara Mileto and David Deutsch call the class where things don't seem to be behaving randomly, they call that class of states sharp with respect to how you're measuring things. And the other class they call unsharp with respect to how you're measuring things. And they use those words metaphorically to evoke the idea of a photo being sharp. So you know that the thing you're taking a photo of, what you're seeing is what you're getting. And an unsharp photo, you may not be sure of what the photo is of if you weren't the photographer originally. But the language there is just to think of it as metaphorically. What they're really talking about is, do things behave with 100% or 0% certainty? That's a sharp state with respect to how you're measuring it. Or do they behave in a probabilistic way? And that's the unsharp state with respect to how you're measuring it. Now, I said with respect to how you're measuring it, one way to interpret that is, what was the orientation of the first film? Right. These angles here are all between two films. Right. So all the photos I showed you of the real films, I was showing you I was holding the film either vertically or horizontally. These two blue directions. I could have held the first sheet at a 45 degree relative to the ground in my room or the ceiling, right? In that case, my measurement axes might be these two blue axes that are 45 degrees to the original photo, and it doesn't matter how I choose my first the orientation of my first film. You'll always get the same sort of red pattern. But the idea that you can have sharp and unsharp states with respect to how you measure it is very important. So here we have sharp and unsharp states with respect to measuring vertically and horizontally relative to, say, the floor in my room. And here's another option to say these are sharp and unsharp states with respect to measuring at a 45-degree angle relative to the floor in my room. And I can choose any set of axes as my way of measuring things. And these concepts are important because quantum information has something in common with classical information. At the start of my talk, I explained that classical information takes some physical system that obeys classical physics, and you form a counterfactual statement with it. And so this photo is the counterfactual statement is I drew the Queen of Hearts, but I could have drawn any of the three other queens of different suits. This happened, but these other things could have happened. And the system that you're building the counterfactual out of obeys classical physics. Quantum information is also a counterfactual statement, but it's a counterfactual statement that uses this concept of sharp or unsharp states with respect to how you measured it. So here's an example of a phrase that is a counterfactual that describes what quantum information is. Instead of a deck of cards, I have my photons and my linear polarizing sheets. And a counterfactual statement could be that this particular photon, its polarization is in a state that is sharp with respect to these two perpendicular directions marked off in blue, but it could have been sharp with respect to any other allowable set of perpendicular directions. For example, it could have been sharp with respect to this instead, or it could have been sharp with respect to any of these smoothly varying two sets of perpendicular directions. I apologize, I didn't draw the blue lines there, but if you imagine the blue lines there, all these other possible perpendicular directions, right? So the counterfactuals, it was the photon's polarization for a single photon, this works. The single photon's polarization was sharp with respect to these measurement directions, vertical, horizontal, but it could have been sharp with respect to any of these other pairs of perpendicular directions that are just rotations of the original. And that is the counterfactual that makes up a statement of quantum information. So classical information and quantum information are both counterfactual statements. They're both manipulations of a physical property that's reversible. And the only thing one of the differences, one system obeys classical physics, the other one obeys quantum physics. And in classical physics, the counterfactual is about things that happened but could have happened. And in the case of quantum information, the counterfactual is about sharpness. It was sharp with respect to this way of measuring it, but it could have been sharp with these alternative ways of measuring it. And that is that counterfactual statement is quantum information. And I studied quantum information for a few years after school. And it took me a long time to come across a concrete explanation of really put your finger on it. What is quantum information? And it took me until I found Chiara's book to say like, oh, I get it. Counterfactuals, but weirder. And the weirdness is this concept of sharpness. So it could have been, this is just a little artistic thing I did. So counterfactual statement, but about sharpness. Now, something that Chiara Merletto and David Deutsch go into in their more technical paper that I cited in the beginning of this talk is part of their paper lays out in their opinions, 9 of the fundamental distinct properties of quantum information, things that distinguish quantum information from classical information. Beyond what, once you understand what I just presented, these are other things that fall out once you understand what quantum information is. So I've listed these in order of like how hard they are to understand and what I really wanted to cover in this talk. So the first one, as I presented in the order, is this concept of quantization. In the case of photon polarization, it has some directionality to it like a toothpick, but its angle cannot vary smoothly in the way that we observe it. So it's this smooth and continuous thing that we're thinking of as a metaphor, the toothpick's orientation, is the counterfactual space shrinks dramatically. And it's this or that in the case of polarization for linear polarizing films. And that shrinking of the counterfactual from smoothly varying and continuous to discrete or lumped and finite, that is called the quantization of that physical property. The other thing, another property, is unpredictability of deterministic processes. For each photon, that bouncer at the club asks the same question of each photon, but each photon might give a different answer each time. We can understand what the odds of the photon saying are and predict what the odds would be. And we can compare our prediction of what the odds should be to observational statistics, and we should see that they match. That's verification that quantum mechanics, quantum theory works. But we don't know what's going to happen for each individual photon. Just like you might know that it's similar to, but different. This is different, but you may know that when you flip a coin, the odds are 50-50, but you don't know what's going to happen each time you flip the coin. It's analogous to that. Number 3 is undetectability of sharpness with a single observation. Again, once you have to understand what sharp and unsharp means. And if you just saw a single photon get through or not get through a pair of sheets, well, you wouldn't know what the odds were. The only way to build up what those odds are is by repeating the experiment many, many, many times. And then, in other words, you want to know, would this have happened every single time out of 1,000 times? If so, then the photon must have been in a state that is sharp with respect to this film. But if you only had one observation, you wouldn't be able to deduce sharpness based on the definition of sharpness itself. Number 4 is a property called consistency of consecutive measurements of a non-sharp observable. In other words, this photo is a little misleading. Imagine you had the three film scenario, and I added a 4th film that was parallel to the 3rd film. So 1, 2, 3 are all 45 degrees from each other, and 4 is parallel to 3. What would happen? Nothing new would happen to any photons that got through the 3 would also get through the 4th one. Number 5, irreducible perturbation of one observable caused by measuring another. Now this photo matches the property well. And so the case of the 2 sheets that are perpendicular to each other, one thing ends up happening, but if I tamper with it in between, with that 3rd sheet sandwiched in between, something radically changes the results of the overall experiment. So I've perturbed means, mess up or change. Right? So that's a photo of that property. And number 6, this is the last one I want to cover. I'm just showing 7, 8, 9 for completeness, but I'm not going to cover those. Number 6 is quantum information cannot be cloned, or in other words, copied. Towards the start of my talk, I explained what copying was in the definition of physical information. But quantum information cannot be copied. And this may sound crazy because we take this that we take for granted that classical information can be copied all the time. The fact that you're watching this video stream and that you're not the first person to watch this video, you're watching a copy of this video. We take it for granted all the time. So it's very strange and maybe shocking that quantum information is not copyable. But if you think about the properties on this list above number 6, you can understand why. It's not magical. It's based on what quantum information is conceptually. So quantum information is a counterfactual about sharpness with respect to a certain way of observing or measuring a quantum system, right? But property number 3 says that you cannot deduce or detect sharpness with just one observation. So imagine you were trying to copy quantum information. You would have to measure it. You have to make some sort of observation. But property number 5 says, but in the act of measuring it, you've messed it up. Okay? So if you try to repeat the measurement, the first one you did messed up, changed the thing that you're trying to measure. So if you were to try to build up enough observational statistics to detect sharpness, you can't, because property 5 and property 3 are messing each other up. And if you can't build up sharpness, then you can't make that statement, that counterfactual statement that is quantum information, that is about sharpness. Okay? So, and that's to me, this understanding for why quantum information can't be cloned, this demystified it for me. The scales fell from my eyes. So in the very act of trying to build up the observational statistics of sharpness, you're messing up the quantum system itself due to property 5. And since you can't build up sharpness, you can't make a counterfactual about sharpness. In other words, you can't copy quantum information. And then, like I said, I'm not going to cover the other 3 here, but Chiara Mileto and David Deutsch do a great job explaining it. It's just really dense. And so what I've done in this talk is try to bring it down to earth and translate it. They also have some nice popular videos where they bring it down to earth in their own way. This might be a topic for another talk. And I'm sorry, because property 9 is another way of thinking about entanglement, which I hope that wasn't the main reason you watched this, but hopefully maybe I'll do another video. So that's a wrap. That's what is quantum information. Thanks for listening.